Okay, so what I wanted to do today, who knows what you need to do for what's due this week? What's due, Griffin?
We need to.
Oh, you got both of them. Okay, yeah, midterm is basically gonna be your, so midterms are gonna be, instead of homework, do the midterm. I'll give you a sense of what's gonna be on it. Basically, think of it as, just kind of anything from mechanics that we've discussed will have the potential to be on it. The main exception that I'm not gonna include is collisions. I didn't give you a homework assignment or particularly many practice problems on collisions, so I'm not going to give you I removed a collisions problem from the midterm. So there won't be anything with collisions. Momentum and impulse will still be on it. We'll go over that today. And then, as Griffin was saying, the other thing you need to do, and this is what gets you all of your engagement points this week, is do the force concept inventory again. Probably not particularly, won't take particularly long. Basically, it's like a before and after snapshot. Do any of those questions make more sense after completing the unit on mechanics than they did before? The idea. So, it's informative. That will not be graded. The midterm, of course, will. But the force concept inventory it's mostly informational for me, basically. So do that, you get all your engagement points. Probably on Thursday, around maybe Wednesday or Thursday, I will post just one lecture on perusal. You won't need to do anything on it this week, but that's where it'll be, just for content purposes. We'll start getting into fluids on Friday. I don't think I'm gonna have, I don't have any class planned for Wednesday. I was gonna give you Wednesday off too and say, consider this your class period to work on the final, is basically what I was gonna say. Now, that said, if people do want to meet with me, I am happy to either meet here or over Zoom. But I'll also post an announcement later today. But if you do want to meet, then just get in touch with me. I have no problem meeting on Wednesday. It's just but I'm not planning on holding class that day. So there you go. But in any event, what I want to do today is go over all the different topics from mechanics and basically mechanics is what we've been doing for the first half of this semester. Everything, motion, kinematics, Newton's laws, forces, energy, momentum, these are all topics that are traditionally included in mechanics. Now, there are a few others as well. Rotational dynamics, we did not cover. That is typically a topic in mechanics. And sometimes waves is as well, although that can vary. We will cover waves later, but we won't cover anything on rotation other than what we did with uniform circular motion. So that is what we're gonna do with that. So first thing that I wanted to discuss was gonna be kinematics. Now, remember, these were basically the rules of motion. Now, the vast majority of kinematics we dealt with constant acceleration. And just so you know, all those kinematics equations that we discussed and that we used a lot, they relied on it being constant acceleration. If you have non-constant acceleration, you need to get into calculus to start solving those, and that's beyond the scope of what I really, well beyond the scope of what I want to cover in this class. So the idea there is that, yeah, for most of the time you're going to be doing the equations. Those will really be, most will be valid when you're going to have constant acceleration. So I'll just define some of the quantities, first of all, just a reminder about some of the quantities. Give you the names and the symbols. Delta X, we also use delta Y for this. This was displacement, as you recall. And basically what displacement was, it was a change in the position, okay? So you found displacement, delta X. The easiest way to find delta X was to do your final position minus your initial position. And in general, these could be vectors. For the most part, you're doing it like more or less in one dimension. So you, I mean, and even when you're not, you can break it down into one dimension. So, you know, you can break your two-dimensional components into two separate one-dimensional component problems. So we typically do it just, you know, x final minus x initial to get your displacement. Same thing with delta y final minus y initial. That's where that comes from. Next one I wanted to talk about was V bar. And this is average velocity. Now, this one wasn't something that we used a whole lot of, but it turns out it can be kind of useful if you know that you're dealing with constant acceleration. So, and I'll give you a couple of the equations, maybe I will. I'll give you a couple of the equations that are relevant for average velocity. So V bar, the simple one is it is just delta x over delta t. Now, this is sometimes a formula people will just use for velocity. Strictly speaking, this is your formula for average velocity. If you don't have an acceleration, if the thing's just going at constant velocity, then this is also your formula for velocity, because in that case, your average velocity is your instantaneous velocity at all points. However, this formula works even if you are using, even if you have an acceleration, okay? So you can always just do delta x over delta t, and that will give you an average velocity. All right, that's a worthwhile thing to remember. Now, the other thing, this one, this actually does require constant acceleration. It turns out that first one I gave you, it doesn't require constant acceleration. Like you can do this to find your average velocity, even if you had a changing acceleration. The second one is going to require constant acceleration just because of the way things are going to work. But if you are constantly accelerating, basically what this one is saying is your average velocity is going to be halfway in between your lowest and your highest. Okay, so basically what this becomes is it becomes the average of your final velocity and your initial velocity. So you add your final and initial, divide by 2. That is your average velocity. Okay. So questions on that? Now, the other one you might be given is V. This will be an instantaneous velocity. And the two most common instantaneous velocities we have to deal with are V final. So this would be the velocity at the end of the process. Whatever that process happens to be. And V initial, this will be velocity at start of process. Now, typically the way you get these, there are two ways you can get initial and final velocities. The most common way that comes up, and the way that I think trips most people up, is you need to be able to infer it from certain things that are said in the problem. So if you hear the term starts from rest, what is that telling you about one of these velocities? That's giving you information about one of these velocities. If the problem says the object starts from rest. Which one? Initial velocity is 0. Yes. So that is what it's saying. If it starts from rest, it's saying your initial velocity is 0. If the problem says it comes to rest, that means the final velocity would be 0. Another one where this comes up is the high point in vertical motion. At the high point in vertical motion, that is where your vertical velocity has slowed down momentarily to 0 before it goes into the negatives. Okay, so again, figuring out these velocities, from the way the problem is described can be a very useful process. The other way that you can get these is from the kinematics equations. Okay, other than that, there's not a real good way without calculus to determine initial velocity or instantaneous velocities. As a matter of fact, instantaneous velocities is effectively a calculus limit for an average velocity when your delta t gets very, very small. So for those of you that are taking calculus, maybe that makes sense to you. But in calculus, these deltas become derivatives, differentials. And basically what you do is you take the limit for the very small denominator, and that's how you determine an instantaneous velocity, instantaneous quantity of anything. So again, the two ways you get this are from problem wording and from kinematics equations. Next one I wanted to talk about, acceleration. Now, the formula I will give you for acceleration. This is going to assume a constant acceleration, but acceleration is going to equal your change in velocity over delta t. Another way to write that, v final minus v initial over delta t. Now that does assume constant acceleration. If you were to have non-constant acceleration, which again, I'm not going to give you any problems with, well, I guess that's not necessarily true. I'm not going to give you any calculation problems with non-constant acceleration. So any problems that you would use a formula for, this will work to find your acceleration. As a matter of fact, this is, you may recognize this formula is actually just a rearrangement of one of your kinematics equations. Okay, it's a rearrangement of the first kinematics equation. All right, now one we've been using the whole time. Delta t, this is time duration. And basically what we're saying is that delta t equals t final minus t initial. And again, we're just t initial is the beginning, basically the way you can think about it is t initial would be the clock reading at the beginning of a process. T final would be the clock reading at the end of a process. So if you were looking at the process with a stopwatch, your T initial would be whatever your stopwatch read when you started the process. Your T final would be whatever the stopwatch read at the end of the process. Okay, and that's basically what we're dealing with here. Okay, so the other way to think about this, T initial, this is the time when object is at X initial and V initial, okay? And you can do the same thing with final, all right? So basically, it's the corresponding time measurement to the position at the same subscript is basically what's going on there. All right, so questions about any of the kinematics quantities? Hopefully this is a refresher, but questions about any of that? Okay. In that case. Next thing I wanted to give you or remind you of is the kinematics equations. And these are in the formula, the equation sheet. So you can use that equation sheet for your final. You can, I mean, it's basically open book, open up. So what I don't want you to do is to Google the problem and get the answer that way. But you can use any resources that you've developed. And again, I get it. It's take home. If you really wanted to cheat, you could, but you know, you shouldn't. So it is on your honor in this case. Okay, so kinematics equation 1, the most common one we end up, well, I don't know, it's the most common we end up using, but it's one, V final equals A delta t plus v initial. And that could be we could make that a vector equation as well, like those are all vector quantities. We end up using this for both the x and y direction in the kinematics problems. It's true of all the kinematics equations, so worth keeping in mind. Next one, end up using delta x equals 1/2 a delta t squared plus v initial delta t. That one works, and then we have v final squared equals v initial squared plus 2a delta x. Those are the three kinematics equations. Those are, if you know those ones, you can more or less do all the problems that come up. Sometimes it's considered the fourth kinematics equation. It does sometimes make things a little easier. It's an equation with, these all have an acceleration. You can get an equation without acceleration, basically by combining the two definitions of average velocity. So this one we didn't use much, and it's not typically given as one of the kinematics equations, but I'll write it down just the same. Delta x over delta t is equal to v final plus v initial over 2. Now, all that is, if we scroll back up to the average velocity, that's just setting this equal to this. Okay, so that's all that fourth equation I gave you was doing. But nevertheless, it is one that does not have acceleration in it. Okay, so any questions about those? Mhm.
Each of these gravity is 10 meters per second squared.
I will accept either. Just tell me what it is. You're just in your work. Show me which one you're using.
Okay, because during the assignments, they used 9.8
Mhm.
and a number of it wouldn't accept the answer until.
I'd really appreciate it if you could tell me which ones those were. I thought I had entered in either error bars or multiple answers for most of those. So if you could tell me which ones those were, I'd really appreciate it. In this case, I'm grading it by hand. So if you just show me what you're using, I will accept that. Other questions? No. Okay, the last thing to discuss is one I really want to discuss is the velocity time graphs. We could talk about position time graphs as well. That's a topic worth reviewing. Velocity time graphs are going to be more relevant they tend to be a somewhat more useful tool because you can get information about both the displacements and the acceleration from them. So what we have here is I'll do it this way. Velocity, actually. Velocity and okay. So what I have here, I'll just give a simple one like so. Doing this. Now, the question I have for you is that I have a couple of questions here. And we'll discuss all of these, but first question. Can you determine, or how would you determine the acceleration from this graph? Very good, Franco's got it. You get the acceleration from the velocity time graph by finding the slope. Okay? So we find the slope, we can find the, you know, you might say, oh, it's not quite a straight line. Yeah, I do it freehand, fair enough. But you can find the velocity time, or you can find the acceleration from the velocity time graph by finding the slope. How about how to determine the displacement? Very good, that is the area under the curve. So area under curve. Now, you couldn't just be asked, I did sort of ask that, but the point I want to make is if you were just asked, find the displacement, you would need more information. You would need to say, okay, oh, fine, I can do that, but between what two times? Okay, because if you go from, say, the beginning to there, the area under the curve is gonna be different than if you go from the beginning to there. Okay, so you need to know the times in order to find the area under the curve. Okay, so you can't just say displacement, you need to, okay, well, displacement over what time period? All right, because it's gonna change, because this thing's motion is changing, okay? So we would have to be real careful from that. As a reminder, if we wanted to go out to this one right here, what we would do is we would basically have this area right here. And then we would have this area right here as well. Now, one thing to remember, if this would be a delta x greater than 0, because it is above the t-axis, or the x-axis, whatever you want to call that, it's above the horizontal axis. This one right here, this would be a delta x less than 0 because it's below the t-axis. It's that point where we have negative velocity, so that means it's going to have a negative displacement. So if you wanted the total velocity, sorry, the total displacement, you would calculate this one as positive and this one as negative. All right, the questions, yeah. Is that a question? No, okay. All right, one other thing. I'll put this one in red. What would a speed versus time graph look like? As a reminder, speed is not quite the same thing as velocity. They are similar, but they are not the same. So anyone think they can tell me how the speed time graph is going to be different? Right. So basically, if your velocity is positive, it doesn't change. Okay, if your velocity is positive, then your velocity is actually equal to your speed. The difference is when your velocity goes negative. So this portion right here, when velocity is positive, you know, when it's greater than 0, all the way down to 0, it's identical to the speed. The difference comes when velocity goes negative, okay? So when velocity goes negative, we don't really care about the direction. We say the speed, in fact, just goes positive again. So it just increases. So the main difference is it would look like this. So it's more like an absolute value function in this case. Now, the interesting thing, if you have a speed time graph, what you could do is now all of your displacements are positive. Okay, so you were to do this delta x then becomes greater than 0. Now, it turns out that what this is now, it's not a delta x, it's actually a distance traveled. Okay, so when you're looking at speed time graphs, your distance traveled is the area under the curve, and it will be positive, unless of course it's zero, like you could have no speed, in which case you would have no displacement. But here's the thing. If all you have is a speed time graph, do you know anything about direction? Do you have any information about direction at all? You don't, okay? Because the red graph corresponds to the blue one. The red speed time graph corresponds to the blue velocity time graph. And in the case of velocity, we lost some of our displacement because we turned around and changed directions. With speed, that information is unclear. It's not clear that we turned around. All that we're indicating is we went some distance, slowed down to zero, then started speeding up again and went some distance, okay? So speed time graphs don't give you any information about direction. That's something definitely worth keeping in mind, okay? So questions about these ones? All right. So a little longer than I hoped to on kinematics, that's okay.
Get into forces.
Now, in terms of the main skills that I think are gonna be useful for forces, free body diagrams. Okay, now, again, this is not, because this isn't just right or wrong answers. If you have a force problem and you get the free body diagram correct, you'll get most of the points for the problem. Okay, I'm telling you that right now. Getting the free body diagram correct is the first and probably most important step in the process of solving problems involving forces. So if you get lost about where to what equations to use, whatever, think and go back and get your free body diagram correct, okay? Because again, I'm looking for process here, so I will grade your free body diagram. If you've got all the forces marked correctly, correct directions, correct labels, I'll give you, like I say, that will be worth most of the credit for these calculation type problems. All right, so that is worth keeping in mind. Next thing, equilibrium. Anybody tell me what this term means in the context of forces? If you're told this object is an object is in force equilibrium, what is that telling you? Very good, net force is zero. So this means F net equals zero. Now, the thing that's related to is Newton's first and second laws. Newton's. And basically, first law, as a reminder, let's write this down, move the not to. If F net equals zero, A equals zero, very useful if you're told the thing is in equilibrium. If you're told the thing is in equilibrium by its very nature, that means it's not accelerating, okay? And the second law is that it's basically just if F net is not equal to zero, F net equals MA. Okay, now if you knew acceleration was already equal to zero, then you could already say F net was equal to zero. So in some sense, the first law is just sort of a special case of the second law. But nevertheless, these are both the two that generally tend to come up in types of problems. Third law is the law of equal and opposite reaction forces. I don't think I have any third law problems on the midterm, but it's something you could check out. It's something worth knowing. The thing to remember about third law reaction forces is that third law, well, two things. Third law pairs never go on the same free body diagram. Okay, because they are on different objects. They're never on the same object. Okay, so you never put third law pairs on a single free body diagram. All right, so that's why, and you'll see this occasionally. People will make arguments that because because of the third law pairs, forces will automatically cancel out, which means acceleration will be zero. That's a fallacious argument because third law pairs aren't on the same object. Okay, that's the main reason why that argument never works. The second thing to know is that they're always the same type of force. Okay, so if you are dealing with a normal force from one object on the other, the third law pair will also be a normal force. If you're dealing with a gravitational force from one object on another, the third law pair will also be a gravitational force. Okay, so that's the main thing to know about third law and third law pairs. Okay, so questions about that? All right, the two types of forces I want to review are ones that come up in the midterm, so just want to talk about those. Tension forces. Now, main thing to remember about tension forces is that tension is constant throughout the rope, or cable, or string, whatever it happens to be. Okay, now the main rope, cable, whatever. The main advantage this has is that, you know, if we were just hanging like a rock from the ceiling and we knew that this, or a box, whatever, we knew that this box had a, you know, this box had a mass M. And we could basically say, okay, the tension force is equal to mg. That's just an application of the free body diagram. The fact that this thing is not moving, we could say that pretty deliberately. But once we know the tension force down at the bottom, that's keeping the box elevated, we can also say, okay, well, that tension force is constant throughout this rope. So that's the same force that it's exerting on the anchor in the ceiling. So if that anchor is not capable of withstanding that tension force, then it'll rip out of the wall, is the idea. Okay, so that's what I mean by tension is constant throughout. It exerts, you know, if you can find it at one spot by doing a free body diagram, you basically know it everywhere else. Okay, that's assuming, you know, there's nothing breaking the tension, and sometimes there are things that will break the tension. So if someone was holding on to the rope, that would actually break the tension. But in this case, the tension is maintained throughout the rope. Similarly, over pulleys. Pulleys in, you know, these ideal pulleys that we're looking at, all they're doing is changing the direction of the force. They're not changing the magnitude of the force. So again, if you're looking at a system, and we did a couple of examples like this, where we had, you know, pulley, you know, and then it was hanging like so. And then we wanted to know the tension in the middle there. The most common mistake for people to do was to say, well, it's equal to the weight of both boxes combined. Not true. Okay, it's not equal to the weight of both boxes combined. Assuming this thing is in equilibrium, we know that the boxes would have to have equal weight, right? Otherwise, it would move. And the idea is that, well, what we could do is we could find tension there just by doing a free body diagram analysis on this block, right? We has gravity, has tension, those two have to exactly cancel out. The idea then is that everywhere in the rope has the exact same tension. Okay, so that means it has the same tension on the left side, which makes sense because it would have to be holding up a box of the same weight, and it has the same tension in the middle. Okay, so that's something worth remembering when it comes to tension. So question on tension forces. All right. Next one I want to talk about is friction. Now, I'm going to I'll give you the friction formulas, first of all. Kinetic friction, mu sub k, normal. Maximum static friction, mu sub s times normal. Now, the one that comes up most of all, and this is one that people get thrown off on, is when you have a car turning. Now, what's the force that keeps the car in the turn, prevents it from sliding out? Easy hint, it's the force we're talking about now. Friction. Question is it kinetic or static? Static, why?
Because, it would have to move, if it was kinetic, and in theory, it's staying in one place and it's going around the corner.
Okay. You're more or less on the right track. I'm gonna flesh that out just a little bit. The car itself is moving, but the surfaces, particularly the surface at where the wheel is in, or the tire is in contact with the ground, that is momentarily stationary. Okay? And the idea is that, well, the car moves by virtue of the fact that the location where the wheel, the tire making contact with the ground is constantly changing. But while the tire is in contact with the ground, it is stationary relative to the ground. It's not sliding on the ground. You know the difference because, if you lock your brakes up, then your tires do slide relative to the ground. That's when you leave the skid. So that's the idea. So if you're dealing with a car turning, you want to be dealing with static friction. Okay, so that comes up in this context. All right. Now, last thing I want to say about forces is that forces are vectors. And this means that they add vectorial. Okay, so what I'm saying here is if you have F1 in the Y direction, F2 in the X direction, your F net is diagonal. Okay, and it has components in your X and Y direction. So basically the way you would say this is F net in the X is basically equal to F2 in this case. Because F2 is the component that's in the X direction, it's the horizontal component. F net in the Y would be equal to F1, because that's the component that's in the Y direction. Now, if we wanted to find the magnitude, sorry, my right triangle probably isn't very good. I'll indicate that it is a right triangle though. If we wanted to find the magnitude, we would need to use the Pythagorean theorem, okay? Because this would be a right triangle, F1 squared plus F2 squared, take the square root, you get the hypotenuse of this right triangle, okay? And if you wanted to find angles, if you wanted to say find this angle, you could do that with trig. Any other angles, sometimes you might need to use trig, sometimes you might need to use some geometric relationships, whatever, but angles can be found with inverse trig functions. Okay? So questions about that? All right. Big topic so far. Next one I want to talk about rotational motion or uniform circular motion. UCM, we'll call that. Main thing that you're going to want to remember is a couple of things. A sub c, your centripetal acceleration, is v squared over r. So, you're going in a circle with radius r at a speed v. You calculate the centripetal acceleration with this formula. Now, another thing to remember is that your centripetal force, this is in fact equal to your mass times your centripetal acceleration, but it is also a combination of actual forces. The combination of forces from FBD, okay? The main conceptual confusion that people have with this is they think that the centripetal force is a special kind of force that comes into being by virtue of the fact that something is going in a circle. That's not how it works. For you to have a centripetal force, what you have is you have some array of external forces that have the impact of causing a centripetal acceleration. Okay, so if you have a free body diagram, you never put a physical force called the centripetal force on that free body diagram. Okay, the centripetal force is more like a net force than it is a physical force. Okay, it's a combination of physical forces. It's not a physical force in and of itself. All right, so that is rotational motion. Questions about that? Okay, next one, energy. Okay. I wouldn't, if I were you, I would know what goes into this category of mechanical energy. Okay, one is going to be work. Work in our context, really work can in principle change any form of energy, but in the context of mechanics, work causes a change in mechanical energy. Causes change in mechanical energy, ME. Now, know the formula for work. It's basically the energy perspective on forces. It's how does a force impact the energy of a system? How does an external force impact the energy of a system? Another one to know, kinetic energy. You can sort of think of this as the main form of mechanical energy. It is the energy directly associated with an object's motion. Okay, so, you can think of what forces do is they impact kinetic energy. However, when we're in mechanics, we also have potential energies. And basically what these were perspectives that we could take on work done by conservative forces. Okay, so and really what it is, you can kind of treat them however you want. And some of you saw this in one of the problems, the group problems last week, with the hand pushing the block up the ramp. And it was going at a constant speed, so a lot of people correctly identified that the net work done on the block was zero because it wasn't changing its kinetic energy. And that is a perspective that you could take that, if you define your system correctly, that's true. However, you could also say, well, no, this block changed height, so it actually added kinetic energy, or it added potential energy, added gravitational potential energy. Now, the difference between the two perspectives is in the first one, you're basically just treating gravity like it's any other force. And what gravity did is it blocked, some kinetic energy from being added to that block. Basically, it did negative work on the block as it was being pushed up. If you, however, treat gravity as a potential energy, you don't include it as an external form of work. What you say is that external work can also increase the potential energy. All right, so it's a perspective on where you're going to put the energy done by certain things. Okay, potential energy becomes useful because the work done by gravity is path independent. So, we talked about this with the roller coaster. If we were to try and do that with work, we'd have to, figure out the path of displacement. We'd also have to figure out the component of gravity that was in the same path of displacement. However, if we take the perspective of potential energy, we only care about the change in heights, which is why it's a useful perspective to have. It's why it's taught. Okay, so that's the idea behind that. So there's that. Conservation of energy. We'll talk about it. Conservation of mechanical energy is mostly what we do. Now, what I'm going to do is I'm going to give you sort of the big picture one. And that is, if you have some external work on a system, this is going to be equal to your change in kinetic energy plus your change in potential energy plus your lost energy or dissipated energy. Okay, this is basically how we used the conservation of energy in the problems. Now, for a lot of problems, you will have, and they won't always tell you this, but like, for example, those roller coaster problems or the car on the track problems. You had to realize that given this thing is rolling on wheels, it's having relatively little energy being dissipated. So you would ignore this term. So the car on the track and the roller coaster problems, it basically said that what we have here is we have changing kinetic and changing potential energy and no external forces. Okay, we didn't have any external forces, so our work was zero, our dissipated energy was zero. Basically, what was happening is our energy in those problems was getting shuttled back and forth between kinetic and potential. Okay, now you might have a situation where you have an external force. An example of this would be the elevator problem with the motor. In that case, you have the motor doing external work. And basically what the motor was doing is it was changing both the kinetic and the potential. Now, if it doesn't tell you about energy being dissipated, then you would assume it's zero. Okay, so that's where that comes in. All right, so last one, power. This is just some energy over time. Usually it's a work over time, but doesn't necessarily need to be. It could be like an energy dissipated over time. So if you're talking about like the power of a resistor, that's really what's going on. The power being dissipated by a resistor. That's really what's going on physically is the electrical energy is kind of being dissipated into internal vibrations, which are kind of experienced as heat. So if you've ever touched a resistor while it's in the circuit, it gets warm. The more current power you dissipate through, the warmer it gets, the faster. So that's the main one. Last thing to talk about. Last thing to know. Momentum and impulse. Momentum was P. And that was just equal to mv, that is a vector, of course. And then your impulse was F delta T. And this was always equal to your change in momentum. Okay, so both like the work perspective on energy, that's how forces impact energy. The impulse perspective on momentum, that's how forces impact momentum. And the reason why we take these perspectives is it turns out energy and momentum are both conserved quantities. Okay, now the way in which they're conserved and the usefulness in which and how we're going to set up those problems is a little different. Like I say, I didn't include any conservation of momentum problems on the midterm, so don't worry about that because we didn't have much practice with that. So it'll just be impulse and momentum. Okay, so I finished my review with a whole 2 minutes to spare. Any questions? All right. In that case, as a reminder, I'm not planning to have class on Wednesday. So if you want to meet either in person over Zoom or over Zoom, I will block time for that, but I'm not planning on meeting here. Okay. Consider Wednesday your class period to work on your midterm. Questions? All right, cool, guys. Thank you. Take off. I will see you all either this afternoon or Wednesday afternoon, depending on which lab you're in.